Okay. So my name is Besien. I'm from APL, where we host this workshop every other year. I'm in the flight software group. We recently concluded an investigation regarding the use of model-based autonomy for Solar Probe Plus. This talk is intended to be a follow-on to Justin Thomas's talk from last year, except taking into account some of the progress and conclusions we've reached over the course of the past year. So this is how I'm going to structure the talk. I'm going to give a mission overview, an introduction to its science objectives, some interesting properties of the spacecraft, and then I'll talk about the scope of autonomy, how we understand it, how we bound and scope that problem, and then some of the challenges that Solar Probe will face operating so close to the Sun. I'll then give I'll give an overview of our traditional rule-based autonomy system, a little history of it, how it's used right now, and then I'll talk about some of our motivations for wanting to explore this model-based approach to autonomy, and this will involve giving a few screenshots and overviews of some of the technology we made to enable this. I'll wrap up the talk with a trade study that we conducted earlier in the year, doing an analysis, a relatively formal analysis of both the model-based and rule-based approaches for Solar Probe, and then I'll talk about the future developments of each of these. So to cut right to the chase, we decided to proceed with using our traditional rule-based autonomy system. The biggest motivating factor for this was its extensive and successful operational history, and it will enable substantial reuse from other missions, most recently the Van Allen probes mission. And then there are other program-specific constraints that motivated this, primarily the motivation to minimize risk by minimizing the amount of new deployed technologies on Solar Probe. But it's not the end of the road for our model-based approach. It has a few other projects lined up for it, including UAV systems, potentially applications to cybersecurity. And then we plan on importing some of the benefits that we've observed from this model-based approach into the continued development of the rule-based system, which boils down to formal verification and the ability to very intuitively see the connections between different parts of the autonomy system. Okay, this picture here was actually taken by the Stereo spacecraft that APL operates. It shows the solar corona. It's actually not appearing too well on the monitor. It shows the sun illuminating the solar corona, which the Solar Probe mission is going to fly straight through. It's going to fly a little further out than what's illustrated here. I read an interesting brief of the Solar Probe mission, and they described it as a mission that will significantly contribute to our ability to characterize and forecast a solar radiation environment. So that consists of four main objectives: understanding the structure and dynamics of the solar magnetic fields at the source of the fast and slow solar winds, tracing the flow of energy that heats the corona, which is actually substantially hotter than the surface of the sun, understanding the mechanisms and flows of energetic particles around the sun, as well as the dusty plasma phenomenon, which is very interesting. It actually consists largely of remnants of sun-grazing comets and asteroids that are in the granular remnants that are embedded in the plasma that surrounds the sun. In fact, the same phenomenon can be observed around the Earth, too. So this is an overview of the spacecraft itself. The main mission will take about 7 years. This will involve, say, 24 orbits of the sun. There's no deep space maneuvers, but it will fly by Venus a couple times to shed some orbital momentum and bring its orbital altitude down a little bit. So by the final few orbits, we'll be within about 4 solar diameters, which is about 0.04 AU, or 4% of the distance between the Earth and the Sun. It's 3-axis stabilized. Again, no deep space maneuvers. I think one of the most noticeable features about Solar Probe is the heat shield, the solar, it's called the TPS, a thermal protection system that'll maintain a 2,000 degree heat difference between the front of the heat shield and the shade in which the spacecraft will reside. The spacecraft bus is separated from the TPS by a set of radiators that'll try to shed some of that heat before it gets to the spacecraft. Somewhat interestingly, Solar Probe can be thought of, somewhat interestingly and ironically, Solar Probe can be thought of as a power-constrained mission. And that's because you can't fully deploy the heat shields because they'll probably, the solar arrays, because they'll probably melt if they are perpendicular to the sun. So they have to be carefully controlled to always be at a very oblique angle from the sunlight. And then, in fact, during the closest parts, have to be within the shade of the thermal protection system. And they're actually 2/3 fully reflective, so only 1/3 has solar power generation capabilities on it. It has a suite of instruments. I'm not terribly qualified to talk about those, but they're intended to enable the scientific objectives. Launches in 2018 on an Atlas V. Okay, so what are some of the challenges that we anticipate for autonomy for this mission? We have a number of communication eclipses that'll accumulate to about 34 days throughout the orbit. Each orbit will take about 88 to 150 days. And we have a very low emergency downlink rate. The last figure I heard was about 8.7 bits per second. Only, I think, that I know of, Voyager has a lower downlink rate. But this is only for the emergency mode, or it's the emergency downlink rate. It'll be substantially faster during other times. So some of the main drivers for onboard fault protection that might stimulate a fault protection response is the need to maintain this pointing of the thermal protection system at the sun to ensure that no part of the spacecraft leaves the shade of the TPS. And as I alluded to earlier, avoiding solar array overheating by ensuring that the solar arrays are always at a very oblique angle to the sun or safely within the shade of the spacecraft. And we have the additional constraint that autonomy must recover the spacecraft into an operational state during very close approaches to the sun. And some other essential requirements: managing the design complexity, executing predictably and robustly, and providing high levels of verifiability, each of which I will talk about further on. Okay, so a former fault management autonomy system lead at APL wrote a very interesting article a few years ago in the APL Technical Digest. He characterized 3.5 generations of autonomy at APL, starting with generation 0, in which there was no notional separation of autonomy from the core flight software. And it wasn't until ACE, which I think launched in 96, 97, where it was first observed that the autonomy subsystem was separate. How do I say this? It was the first time autonomy separated from the core flight software. And it was a relatively simple system. It consisted of 64 rules. Each rule monitored a certain or particular telemetry point and then had an associated response should that telemetry point cross some critical threshold. With the second generation of autonomy systems, this is seen on the APL spacecraft near and timed, it allowed for more expressive conditions to determine if a fault had occurred. So rather than monitoring a single telemetry point, it could monitor several in some logical expression and allow for a more nuanced detection of faults. In the third generation and on, this is seen on the APL stereo messenger and Van Allen probes mission, we saw even more expressiveness and the ability to detect faults. And then we introduced notions of computed telemetry, storage variables, and the expressiveness of the overall autonomy system increased dramatically. Rules could enable and disable other rules. They could write to variables. There could be a more guided response to faults on board. So this is the current state of it. When I say single fault tolerant here, it's not so much that the autonomy software can't respond to anything more than a single fault, but our expectation of autonomy is that it should only handle a single fault. If nested faults happen or some sequence of faults, we don't expect autonomy to fully respond to that, in part because it's not clear what a good solution is to that, and it's also very difficult to ensure that a response to a nested fault is correct and won't exacerbate the problem. So our autonomy system now has allocations for dozens of RPN expressions that are used to detect if a fault occurs, computed telemetry points, which are essentially expressions of telemetry points. They're telemetry points that come from other telemetry points. So in your expressions, you don't have to do a full expression. You can just reference one of these computed telemetry points and storage variables that autonomy rules can write to save their state or the status of their response or any number of things. And it allows fine-grained manipulation and control, particularly by the mission operators who can enable and disable rules, upload new ones, remove them, clear them, have a very fine-grained control into that. What I show on the right is what the autonomy system looks like from the point of view of mission operations. So this is just one view. You can see on the bottom there are several tabs. So this page right here shows the counters. So how many times certain rules have fired. There's many other views that the mission operator can use to get insight into the state of the autonomy system. From the point of view of the autonomy system engineer, this is what some of the documentation looks like for the autonomy system. I believe this is for a star tracker. I'm not sure which mission. Each set of 3 rows corresponds to a certain autonomy rule. In the first row, you can see the index, and the second row is the title and description, and then the third row is the rule premise, and that's the expression that will determine whether or not a fault has happened and a response should take place. And it's pretty nice. This is an HTML document. If you're not sure what a certain mnemonic is, you can click on it and drill down, get a deeper view of it. There are several other views of the autonomy system. This is just one of them. And one of the things that we wanted to explore in this investigation is what if we replace this view with this? And this is a screen capture from our model-based autonomy designer software. There are many levels of details you can use. This one is a more restrictive level of detail, so it's not showing all the connections. And this is also for a star tracker as well. And you can see the star tracker, the state machine for the star tracker starts in the initialized state, and then it's very clear to see the subsequent states that the star tracker can be in just by following the arrows. And then if we were to enable a more complete level of detail, we'd be able to see these expressions down here, what condition or what transitions they drive, the transition being the arrow that connects 2 states. And then it's very clear and very intuitive to see, first of all, see how you can enter fault modes and the next mode that, the next state that the system is, can be in. So this is something I'm going to continue to talk about throughout the presentation. What are the principles of autonomy system design? In that article I alluded to earlier by George Cancro, he said there are 3 main principles: understandability, flexibility, and verifiability. Understandability necessary for reviews when you have engineers of many different backgrounds, systems engineers, software engineers, other stakeholders. It's important to have them all have a unified view of the system and not hold separate conceptions of it. Flexibility, in part because the mission ops team needs to have this granular control over the autonomy system to enable, disable rules, things like that. and verifiability, just to reduce the risk and prevent a crunch in INT testing that I'll get to in the next slide, I think. So more of our motivations for taking this model-based approach. In 2008, there was a NASA fault management workshop. They had a number of findings, I think a few dozen, but there were two in particular that we sought to address with taking this model-based approach. First was the downstream testing crunch, and it was observed across many institutions and across many missions. There tended to be a spike in fault management spending during the INT phase. And the reason for that is because it was very difficult to test the autonomy system before a full hardware test bed was available. So it was kind of pending on this full test bed to be available. And then when it was available, then a lot of money was dumped in and a lot of work was done testing it. And so one of the recommendations that came out of this workshop was to somehow solve this problem and enable testing earlier on, not necessarily to reduce the overall cost, but to smooth out the spending rate on fault management. The fourth finding that was relevant to us noticed the lack of sufficient formalization and nomenclature in fault management designs and documentation. And the recommendation there was to identify techniques to improve the fault management system design and review. And I think it'll be very clear how the model-based approach addresses this concern in particular. So getting back to the three principles of autonomy system design I mentioned earlier, how does our model-based approach seek to address them? So for the principle of understandability, in a model-based system such that we propose, the design is the implementation. There is no drawing or no Visio diagram in which an autonomy system engineer has to look at it and then form some understanding of it and then actually enable it, write all the rules by hand that he thinks or he or she thinks will implement this design completely and soundly. Essentially, there's no interpretation of the design. And then from the point of view of mission operators or other stakeholders, it provides a much more intuitive view into the state of the autonomy system and where it's likely headed. And I think in the previous slide, that should have made that a little more clear. Flexibility, the idea here is that a mission operator, for instance, or an autonomy system engineer can go in, click on a state, make that the active state, manipulate inputs, enable or disable rules, all with the click of a mouse, and essentially alter the behavior of the autonomy model on the fly. And then the third major principle of autonomy system design is verifiability. So our model-based approach seeks to address this in two ways. The first of which is to enable early testing without testbed integration. The second aspect is informal verification, and the fact that by its very nature, a model-based approach is a state machine, which is a formal, well-studied structure in computer science. It's much more amenable to reasoning about formally and running through model checking and formal verification methods. So execspec is the name of the software that we developed to enable our model-based approach. The core concepts were developed not particularly with application to Solar Probe. It was developed independently by George Cancro, who used to be the autonomy system lead in our group. This was around the fiscal year 06 to 09 timeframe, and the work was done under a number of internally funded projects. It's based upon the notion of the Bell Labs virtual finite state machine. And at risk of oversimplifying, I think it might be able to be described as a generalization of a finite state machine with the ability to handle both synchronous and asynchronous inputs that would drive a state transition. So the execspec, which stands for executable specification software suite, consisted of three main components. The first is the design tool there was an interpreter and a visualizer. The design tool, as it says here, intuitive visual programming for state model logic through diagrams. And what I showed in the previous slide was a screen capture from the designer. It wasn't a picture of the full window. It was just one frame in it. But it enables kind of like Visio, an autonomy system engineer to create a new state machine or set of state machines with states, with various inputs that are tied to the spacecraft telemetry, and then connect the various states and describe how they transition. The interpreter takes the model that was provided by the design tool and executes it. And the idea is that the same code, the exact same interpreter instance, not instance, the same interpreter software will run both on the spacecraft and internally to the designer. So there's no separate implementations of it, say in C, one in C and then in Java. There's just the one. And then there's a visualizer, which is expected to be run in mission operations environments, and it's a tool to provide situational awareness to the mission operators. And it will receive telemetry from the spacecraft and then highlight and animate the current state of the spacecraft and make it very clear to those on the ground what's happening on board the spacecraft. So it's kind of interesting. A lot of people approach me when I'm talking about this who are in the group but maybe not familiar with this work, and they say, why not just use model-based autocoders? And in fact, I think as we've seen at this workshop so far, they've been used to great success. And so I think it's a very reasonable question, why don't we just use model-based autocoders? And the reason basically boils down to our concept of operations. It would not support that. Taken from a brief that was done last year, 2 years ago, these alternatives do not provide the end-to-end flexibility and operations monitoring capability necessary for us. First of all, it's the desire to separate the interpreter from the autonomy model. So we have as I mentioned in the previous slide, we have the interpreter, which will take a model from the designer, and if we were to use some model-based auto-coded method, both the model and the interpreter would be the same piece of code. And I think in a presentation yesterday, the speaker made it clear that patching these things is not easy, and we expect to do a lot of patching, or what would be called patching, basically uploading new models, manipulating those models at runtime. And also, it might not provide the capability that we would like in the visualizer, which is to listen to the spacecraft telemetry and then animate what's going on. So this is the process we took to investigate our model-based approach's suitability for solar probe. Early on, to motivate further study, there was a concept development IRAD on stereo, in which the stereo autonomy system was basically translated into exec spec, and we demonstrated that it successfully handled the requirements of the stereo autonomy system. And then in the past year or two, we had this investigation. First, we did a integration prototype integrating the exec spec interpreter into our flight software CFE environment. And then we had two other efforts ongoing at the same time. We did a tech readiness demo on a UAV, and concurrently with that, we had a formal verification IRAD. And then at the conclusion of the investigation, we did a trade study that did a pretty formal comparison of the two approaches and issued its recommendation. This is a concept of operations in a nutshell for exec spec. I think the laptop might not have been the best choice here, but the idea is that the autonomy system engineer will design the model and then upload it to the spacecraft, design or alter a model, upload it to the spacecraft. The exec spec interpreter on the spacecraft loads this model, executes it, takes telemetry from the spacecraft, issues its commands if necessary when responding to a fault, issues the flight software commands, and then puts the telemetry back on the bus, which are sent down on the software bus, which are then sent down to the ground and then used to animate the designer or visualizer so the analyst on the ground can see precisely what's going on. This is a more complete view of the exec-spec designer. I'm not going to go through every single part here, but the central portion, the autonomy system engineer can create a new state. He can create nested states, states of states. These are inputs that are drawn from the telemetry points. And it also enables playing back of telemetry, so you can record telemetry for a little while, and then using some of these buttons here, you can rewind it, you can play it, you can run it, so it's using canned or recorded telemetry, and then you can manipulate some of the inputs to see how the behavior of the state changes due to unexpected events. And this goes a long way towards enabling what I alluded to earlier, which is testing early and not being contingent on the development of a full hardware test bed. So modeling stereo, one of the first IRADs for this investigation. What you see on the left is the zoomed out big picture view. This is the set of 43 state machines. And what you see on the right, that's the same diagram as earlier, but it's one of these state machines except when we drill into it. And what this provides is a much easier way to view the interconnections between different parts of the autonomy system that isn't necessarily available to us if we're taking the traditional rule-based approach. So in this effort, the stereo autonomy system was translated into 43 state machines. We went into the test bed, replaced the traditional autonomy system with the exec-spec interpreter, integrated the visualizer and designer into the ground system, and then demonstrated that this handled a substantial subset of the requirements for stereo fault management. We didn't necessarily aim to handle all of them, and what we set out to achieve was achieved. So after this concluded, we had two other IRADs going on at the same time. There was this formal verification IRAD, and the idea here was to include in exec-spec essentially turnkey functionality for formal verification of the model. So this is a concept of how it would work. You'd start with the requirements. The autonomy system engineer would create the model in exec-spec, and concurrently to that, a set of logic specifications would be created, which you could think of as a set of invariants. And there's an example here, never radiate while swapping antennas, so it should always be the case that this condition is not met. And so then via a plug-in or an extension to the exec-spec designer, the autonomy system engineer could export this into a new SMV model, which is the model checking software we use to do the model checking. And then the idea is that counterexamples would be produced to show that there is in fact a bug and one of your invariants is broken. So the idea here was to import or include this capability into exec-spec, the turnkey model checking. It was successful, and the way it was tested was we took the model and then removed bits of it, and it would cause faults that we know would occur, and then we observed that the model checker did in fact identify these faults. At first it took several minutes, several hours over the course of the IRAD, but by the end, once the procedures were well known and the software was coming together very nicely, we could prove these constraints on the order of several seconds. I was not involved with this one. I was much more involved with the next IRAD I'll talk about. So if any of you have any questions about this later on, I'll try to answer it as best I can. But this particular effort I was not terribly involved with. So the concept here in this IRAD, which took place at the same time as the formal development one, the formal verification IRAD, was to demonstrate the technology readiness level of the exec-spec software in a challenging environment on a UAV platform. So the approach was to develop a fault management design, and the design we came up with was to override the aircraft's autopilot if it entered an anomalous state where it was liable to stall or have some other problem develop. The two cases that we observed was the engine over temperature, which is if the aircraft climbs too rapidly, which would cause the engine to overheat, which could eventually cause it to stop working properly, or if the operator, not so much the operator, but the manager of the UAV would put a waypoint for the UAV too close to its current location that would cause it to bank a little bit too vigorously and then put itself in a potential stall situation. The idea was for our system to detect this and then put the aircraft in a nominal state and then yield control back to the autopilot once the aircraft was stable. So this involved two steps, integrating our exec spec interpreter into the flight software environment on the aircraft, which incidentally was actually very similar to the message bus and flight software architecture that we use on spacecrafts. And then we also integrated the exec spec designer and visualizer into the ground component so we could see very easily when the aircraft entered a potential stall situation and observe the autonomy kicking in and overriding the autopilot. So the first flight test was at a farm in Maryland. This was the aircraft we used. It had about a 6-foot wingspan. And then following that, a few months later, we did a demonstration on a commercial UAV. I think due to some constraints, I probably shouldn't talk about the details of that too much. I will say, though, that it was on an aircraft that had a wingspan of several times that of what's pictured there. So to wrap up this trade study, how am I doing on time, by the way? A few more minutes? Okay. We did a formal comparative analysis of both the model-based and rule-based approach, and we started with what I'm going to call the null hypothesis, which is rule-based autonomy is suitable for solar probe. And the question we wanted to answer through the course of this investigation, does our model-based scheme, as enabled by exec spec, provide a substantially compelling case to overrule this? What were some of the concerns? On a program level, there was really a desire to limit additional new technologies for solar probe. First, because there are already so many new ones, and each new one increases risk. And also to leverage reuse. If we used our rule-based approach, we could reuse almost entirely the software for autonomy. Not the models, but the autonomy engine. So the approach that was taken, the fault management team created a list of several dozen metrics that are important to fault management, and both the rule-based and model-based software were given a score for each of these metrics, and then each metric was also given an importance rating. So the first one was reinitialization speed. On solar probe, we expect to rotate the processors very frequently due to radiation-induced upsets. So the active processor might have some fault, and then the hot spare will have to take over. And it's very critical that while operating so close to the sun in particular, the autonomy system can come back up right away following a processor rotation. So on this metric, the rule-based approach won out. The next one was managing subsystem interdependencies. This is a complex system with many interactions, and sometimes, in fact, oftentimes, when you're viewing the autonomy system in the rule-based approach, sometimes it's not always clear how different components interact with one another. With exec spec, it's very clear. You can sometimes just mouse over and see the connections between subsystems that is not apparent otherwise. So on this account, the model-based scheme came out ahead. Intuitive visual system for reviewing designs. This is when you have many stakeholders in the room of many different backgrounds. The model-based approach came out on top for the design, but for mission operations, actually, the use of traditional autonomy is very well understood, and this model-based approach didn't necessarily provide too much benefit for them. I think the next point is very interesting, designing sequences of several decision points. So this is if you have a response that might take place over the course of several autonomy evaluations that will require checks of telemetry while the response is in progress. For this, the model-based scheme came out ahead, since a fault can itself be one set or one state that has in it several child states, and it can enable great granularity in transitioning from state to state based on certain telemetry. So the model-based scheme came out ahead here. Similarly to that, there are path-dependent responses. So if the response to a fault might involve different paths, or the way in which the fault was entered. I think an example here might be of the solar arrays overheating. Did it overheat because they were deployed too much, or did it overheat because the thermal protection system is pointing the wrong way and the spacecraft is not pointed as it should at the sun? And this is an example where it's not just the fault that's a problem, but it's not just the fault, but how do I say this? Where the response to the fault might be different depending on how it entered that faulted state. Similarity of design to implementation. This is something that will reduce costs and risk. Of course, the model-based approach came out ahead here because, as I said earlier, the design is the implementation. There's no interpretation that needs to be done of a picture of a design to the actual autonomy system. The facilitation of formal verification. This was identified to be important, but it would never substantially replace any traditional testing. So it would add some cost. And then it was observed in the course of this investigation that some of the benefits of formal verification could actually be used in the rule-based approach. So the model-based scheme came out ahead on this, but not by too much. Another very important aspect is the efficiency of implementation. A model-based approach will necessarily require more memory, more time to evaluate the rules and produce responses than a relatively simple rule-based approach. So on this important metric, the rule-based approach came out ahead. Somewhat interestingly is parallel development. There's a well-established process for this in the rule-based approach, where every autonomy object is implemented in its own file. And just like any software development process, autonomy system engineers can check out that autonomy system, edit a file, commit it, and then if there's a merge conflict, it can be very clear when looking at the text how that conflict should be resolved. With the model-based approach using exec-spec, the autonomy system was expressed as a single XML document. And although we didn't have this happen, this was something that we didn't have a good answer for. What if one developer checks out the code, makes their modification, another developer checks out their code, makes a modification, commits it, and then the first developer tries to go ahead and commit their changes, and there's a conflict? It's not clear for several reasons how that should be resolved, especially since it's going to be XML. Sometimes it might not be clear. It's automatically generated XML. It might not be clear how to quickly resolve that problem. As for a starting point for testing and implementing logic, the model-based approach definitely came out ahead there because it enables testing at a much earlier phase in mission development than the rule-based approach, which is contingent on having this test bed there. And then the final one, potentially the most important one, is past mission experience. And the rule-based approach has been used on APL spacecraft for many decades, has extensive successful use, and this is valuable during all phases of the mission, and institutionally, everyone from flight software developers to autonomy system engineers to those in mission operations have a good idea how the rule-based approach works and is very comfortable and familiar with it. And then the 2008 fault management workshop that I alluded to earlier, they observed sometimes that teams that switch their autonomy systems and fault management systems midstream, that was often error-prone, problem-prone. So the conclusions, it was observed that both the model-based and rule-based systems are of equivalent expressiveness. The model-based approach offers nothing that can't be done in the rule-based approach, and vice versa. By the formal metrics of the trade study, the model-based approach came out just a little bit ahead. But recall the null hypothesis that I talked about a little earlier. It did not necessarily provide a very compelling case to override that and use. It was not compelling enough to overcome the motivation to remain with the rule-based approach. But this is not the end of the road for exec spec. What we plan to do for the next fiscal year, we'll proceed with the development of the rule-based autonomy system for Solar Probe, although we'll leverage some of the benefits that we identified throughout this investigation. Essentially, that boiled down to formal verification and the ability to identify unapparent connections between different parts of the system. And we're going to leverage those benefits and see how they can be included in this rule-based software that we'll be using. This is our diagram of our flight software architecture that we often show to Am I out of time?
Close.
Okay. All right. This is what we call the lollipop diagram. Each one of those lollipops up top is a flight software application. It's hard to see the color contrast, but those in white can be reused as is from previous missions. The ones in red have to be developed, have to be redeveloped for Solar Probe. And then Autonomy is one of these that can then be reused directly as is. So what's the plan? What can you expect to see in FSW 2014? For ExecSpec, which was our model-based software, you can expect to see some reports on its application to UAV systems, cybersecurity, situational awareness. That's a very interesting aspect of it we think it can be used for. And then future space missions, probably CubeSats, things like that. For Solar Probe, you might be able to see a report about how we leverage some of the features on ExecSpec, the turnkey functionality of formal verification, for instance, and see how that can be leveraged and used on the Solar Probe rule-based autonomy system. So that's it. This investigation was a result of many people, only part of which are listed here. I'd encourage you to look at some of these articles that have come out in the past few years to get a better background. So that's it. I apologize if I've gone over time. And
Are there questions?
Other questions?
No? Okay, thank you.
Thank you.